The goal was to create an encryption which was unique to the password and thus could only be broken by someone who knew the password rather than knew the encryption method. Since every encrypted message can be different based on the message or the password, the brute force method of testing various inputs is nearly impossible since the attacker would have to not only test every possible message but also test every possible password. The number of possibilities that would have to be tested would scale a rate of c times 27 to the m plus p, with m being the number of letters in the message and p being the number of letters in the password, c being the time it takes to encrypt one message. So with a 10-letter password, and assuming c is equal to 1 second, it scales up fairly quickly. The graphs on the screen are graphing number of characters in the message across the x-axis and time required for a 10-letter password to be brute forced on the y. Black being with 1 character message, red being 2, blue 3, green 4, and orange 5. If we scale this up to having a 10-letter password with a 10-letter message, it will estimate to be about 4.2 times 10 to the 28 seconds, which is 100 billion times the age of the universe. That is only with 10 characters for a password, let alone something like 20 with no cap on the max size. So the method is as follows. Step 1 is to generate a sequence number that is unique to the password, i.e. password would be something like a 64-digit number with starting with 0717, etc. Step 2 is to generate the key value pairs using the proprietary algorithm, which creates the connections based on the sequence number. Step 3 is to apply a one-to-one swap of the keys and values, which is a substitution cipher. Step 4 is to analyze the distribution of characters in the encrypted message. Step 5 is to automatically determine the appropriate way to neutralize the message, i.e. add filler characters that disrupt the message and prevent character analysis, which we call the Scrabble method. Statistical frequency analysis, which is commonly used to break substitution ciphers like the one we applied in Step 3, is foiled by this step. Step 6 is to calculate the unique neutralized numbers and insert the message using a similarly encrypted tag. Step 7, which is optional, is to apply the encryption on itself, to further randomize as many times as you'd like, since the encryption can be applied recursively. In order to keep the scaling low, our cipher program will only apply this once, but this can be overridden using the public encrypt and decrypt methods to allow as many times as needed. The encryption is accomplished by undoing each step in the reverse order.
In order to run the cipher, we can execute the runnable jar in the terminal or command prompt using the Java command line. In the command line, if we want to run the jar file, the command is java -jar and then the path to the jar file. You can simply drag the jar file for this. Now, firstly, the cipher will ask you for a password. The longer the password, the stronger the encryption will be. However, every password will produce a unique substitution cipher. Once that's done, you can now type the message that you wish to encrypt and hit enter. After this, the cipher will tell you all the steps that it applied to the message, and then it will provide you with the encrypted message. Now this message can only be decrypted by knowing the original password. If we try and type a password that's different from the one that we used to encrypt, it will give us an error. Lastly, if we type the correct password, it will undo all the steps properly and provide the message we typed in. Ta-da!